Hello, everyone. My name is Omar Farhat, and I'm a master's graduate from the University of Waterloo. Today, I'm excited to present Klink, a progress-aware scheduler designed for streaming systems. Klink aims to rapidly propagate events to output operator while performing judicious memory management. Internally, Klink robustly infers stream progress from multiple factors, including pipeline semantics, watermark progress, and network delay. As we later demonstrate in the paper, Klink achieves a general reduction of latency by 60% and 20% throughput improvement. This paper is joint work with Professor Khuzaima Dodji from University of Waterloo and Professor Leonardo Curzoni from Sapienza University. Stream processing engines, or SPEs for short, are designed to continuously ingest events and compute output. Events ingested by the SPE could be generated from multiple sources or applications, including sensor data, transactions, and logs. SPEs are also designed to continuously output events. Queries deployed over the SPE could vary in complexity. They could be as simple as calculating the average temperature received in the last 5 seconds, or as complex as detecting security fraud in database transactions. Subsequently, the SPE query could send its output to multiple destinations, including applications, event logs, and databases. SPEs experience many challenges that may hamper their ability to rapidly process queries. These challenges include large pipelines, where query could contain multitude of operators, as in many real-world use cases, heavy input loads, where the SPE could be expected to ingest as many as millions of events per second, and fluctuating or unpredictable load spikes of input workload, making it hard for system designer to provision sufficient resources and thereby degrading the SPE performance. This contention in the SPE caused by the three previous challenges forces degradation of throughput and overall end-to-end latency, which could lead to violation of application service requirements that impose tight deadlines for output generation. SPEs provide event processing semantics where streaming queries are defined by multiple processing units called operators deployed over one or more computing nodes. In this example, we see three operators: source, window, and output. While the source operator ingests events, the output operator transmits events to demanding applications. To process computation on a stream of data, SPEs provide semantics for grouping events that exhibit common properties into structures called windows. Windows provide flexibilities for query through hosting complex grouping selections. Here we can see a block window waiting to be processed, as indicated by the stopwatch. Consider in this example the tumbling window that groups events received during the last 6 seconds. And consider that at t equal to 0, the time at which the pipeline was started, the window cannot process its events because the input is not complete yet. We should wait for at least 6 seconds to have some guarantee that events were received and ingested by the pipeline. At t equal to 6, the window had waited for the events generated within the last 6 seconds, process them, and then send the output events to the output operator. At t equal to 7, the window is waiting again to ingest events generated between t equal to 6 to t equal to 12 before processing them. As can be seen in the earlier example, output can be generated only after the window time is due to be processed, after the window deadline. Latency could therefore be defined as the time at which output events were processed and emitted by the SPE minus the time at which events relevant to the windows were all collected. How does the SPE know when all input events were collected? Consider the following example, where a window operator is grouping events generated within the last 6 seconds. Here we can see 4 events are queued by the window operator. The first being generated at t equal to 1, the second at t equal to 3, the third at t equal to 4, and the fourth at t equal to 5. Now in this example, we observe that after some unpredictable time, the event generated at time 2 is finally received by the operator, long after the events were t equal to 4 and t equal to 5. Event 2 is considered to be a straggler or also as late event. Delays could be due to network delays, most prominently, or malfunctional events generator. In this situation where an event is late on a windowed operator, the SPE has to wait for receiving the late event and produce to correct the output, incurring a large latency penalty. The question is, when should an operator close the current window and produce the output? Watermarks. Watermarks are in widespread use in pipelines encompassing window operators that indicate that no further events are expected beyond a certain timestamp. They are used in lots of streaming systems, including Apache Flink, Apache Storm, Sansa, as well as Google Milui. In this example, upon receiving watermark 6, the window operator is informed that no events generated before time 6 are longer expected. Therefore, the window can safely process the 5 queued events. Watermarks could be generated by the SPE via ad hoc function like periodicity or based on analysis of delays encountered by events based on the source. The most common use case is to periodically generate watermarks. However, even in periodic functions, watermarks cannot be generated immediately. In this example, watermark at t equal to 6 should not be generated because it won't account for network and other delays encountered by input events transmission. As such, watermarks were designed to determine input completion time and therefore time at which window can process its events. Latency could therefore be defined as the time of processing output operator minus the watermark ingestion time. Note that the watermark ingestion time is not within the control of the SPE. However, the processing output operator delay could be minimized as much as possible. If we are to design a scheduling algorithm for streaming systems that minimize output latency, it needs to be proactive in terms of estimating watermark ingestion time so that we use the watermark ingestion time predictions to schedule events relevant to the window operator. To address the scheduling problem, we have designed Klink, a runtime scheduling algorithm that proactively estimates watermark ingestion time and accordingly selects query for processing. The slides presents the overall architecture of Klink. I will present the key components next. The first stage is runtime data acquisition, where Klink schedulers collect the necessary information from operators and pipeline to proactively estimate deadlines and prioritize queries. Consider the earlier example of having a deployed query containing 3 operators. As mentioned earlier, each operator is runnable as a thread. Klink scheduler communicates with each thread responsible for the processing of an operator to collect the necessary information. Specifically, it collects network delay from source operator, which is measured by time of ingestion event minus time of generating the event at the source, the queue size of each operator, the cost of seconds of processing the queue, and as well as selectivity. After collecting the necessary information, we discuss in the next stage how queries are prioritized in Klink. Klink utilizes the least slack policy that is used in real-time systems where multiple deadlines exist, and the system goal is to minimize missing deadlines as much as possible. The least slack policy, simply stated, is defined by the following: slack equal deadline minus cost, where deadline is the watermark ingestion time, and cost is the cost in seconds for processing all queued events relevant to the window operator. Slack as a quantity, therefore, is the amount of time at which an operator can sit idle without processing events. The less the slack, the higher the priority of the query. Consider the earlier example now of 2 queries, the top one running 3 operators while the bottom one containing 4 operators. Each of the 2 queries contain a windowed operator. The stopwatches represent watermark ingestion time. Now say we know when the watermark is going to be ingested, and say that query 1 is going to ingest its watermark after 5 seconds, while query 2 is going to ingest its watermark after 3 seconds. Say the cost of processing queued events in Q1 is 4 seconds, while the cost of processing queued events in query 2 is 1 second. The 2 processing numbers imply that query 1 has much higher demand of processing capacity for its queue. The slack of query 1 can be computed as watermark ingestion time minus cost, which results to 1 second, implying that query 1 can sit idle for 1 second without processing, or it will miss its deadline. As for query 2, the slack is estimated at 2, implying query can sit idle for 2 seconds without missing its deadline. At that specific point of time, query 1 had higher priority than query 2 due to lower slack. Therefore, it is prioritized for processing. In this example, we saw that Klink strives to minimizing slack, whereby it's actually minimizing the number of events queued so that when the watermark is ingested, it can quickly flow from the source operator to the window operator, pushing the output events therefore downstream. As previously stated, most of watermarks are generated on periodic basis, where period is usually let know for the streaming system. Therefore, the watermark ingestion time could be modeled as periodic rate of watermark generation plus the incurred network delay by an event before its reception by the SPE. Because of network delay function, and by the law of using large numbers, the time of watermark ingestion could be modeled as a normal distribution. Using this function, we can determine with very high accuracy the time at which the watermark will be ingested regardless of the network delay. When R, the parameter representing the network delay, is in milliseconds, is set to 0, then the watermark ingestion time is equal to the deadline of that of the window. In real-world scenarios, this is very unlikely, and the normal distribution captures this information quite accurately. R is used as a unit to determine at which range the watermark could be ingested. For instance, using the normal distribution, we can estimate what is the likelihood of ingesting watermark between deadline plus R and deadline plus 2R. Specifically, looking at this figure, using normal distribution for each range in the distribution, we can estimate the likelihood of ingesting the watermark between these time periods. The probability of ingesting watermark between deadline plus R and deadline plus 2R could be represented as such. Then, to estimate the watermark ingestion time through taking the summation of each probability of likelihood higher than epsilon. The deadline could be estimated as the probability of ingesting the watermark at that specific range times its weight. After collecting the network delay, ingestion time could then be estimated and therefore the slack of each query. Klink is composed of two scheduling policies. Klink not only prioritizes queries to be processed based on the slack policy, but it also handles memory management so that the system performance is never throttled. Specifically, some operators, like window operators, need to store transient states in order to fully process input events. This requires extra memory storage. And if memory becomes a scarcity in the system, a huge contention could be imposed, and therefore it doesn't only block the system from running and processing events, but also from ingesting events. As we demonstrated and proved in the paper, scheduling policies that does not prioritize memory utilization, including slack, could reach a level where it is unproductive to the system due to the high memory resource contention. Klink resolves this problem through implementing a scheduling policy to minimize memory utilization after reaching a threshold B, which is well defined in the paper. Next, we explore through an example the functionality of Klink memory management algorithm. Consider the following example running 3 queries, where we can see here the number of events queued at some operators. In query 1, we can see that the source operator queued 30 events, while for query 2, we can see 20 events are queued at the filter, while for query 3, we can see 30 events are queued. Consider that in query 2, we see that the selectivity of filter event is 10%, implying that 9 of 10 events are dropped at the filter. This operator reduces significant memory. While for the window aggregation, all events are effectively reduced to 1, which is the aggregated sum, implying events could be reduced up to one specific event. The scheduling of that specific operator is also encouraged by the memory management algorithm. The scheduler would look at query 1 and determine that scheduling this query for processing would not reduce events. While for query 2, based on the estimation of 10% selectivity, we can project that the number of events processed after processing the 20 events to be 18, resulting in significant reduce of memory utilization. While for the third query, we can expect the 30 events to be aggregated into one final event, that is the running aggregation of the events. For instance, consider this operator to a summation operator. Then the total memory needed for the single event is the sum of the 30 processed events. The scheduler algorithms determined that query 3 reduces the memory the most. Therefore, it was selected to be processed. If the scheduler algorithm determines that more memory need to be freed, it would select between queries 1 and 2 to be processed. Since query 1 does not reduce memory at all, query 2 was selected, freeing an additional 18 events. The scheduling algorithm freed as much memory as possible from the 3 queries. Overall, based on multiple factors, including selectivity of operators like the filter, the queue size, the operator type, as you have seen like aggregation, we selected the queries that reduce memory utilization the most incrementally until enough memory is freed, and the system can run without any performance throttling. After running one of the 2 prioritization algorithms, Klink selects the queries to be executed and accordingly processing events. Then, after some time, Klink cyclically evaluates and operates the scheduling strategies I described. In the next section, we will discuss the experiments run on Klink. Klink is integrated into the SPE Flink, hence the name of Klink. Flink is open source and is well used in the industry. We tested against 3 different benchmarks: the Yahoo Streaming benchmark, the Linear Road benchmark, and the New York Taxi benchmark. In the paper, you can find the results of all 3 benchmarks. However, in the slides, for the sake of time and simplicity, we will only show results of YSP. We compared Klink against algorithms like default, which is basically Flink's default scheduler, the round robin policy, where each query is designated for processing every quantum of seconds, and the first come, first serve selects the query with the earliest event and then schedule it for processing. We also compared Klink against most prominent scheduling solutions found in the literature review. The highest rate, based on the selectivity, cost, and pipeline, determines the query to be processed. Highest rate has shown to minimize latency for queries with no windowed operators. The streambox policy is used in the streambox SPE, where streams are divided into substreams, each of which is parallelized and prioritized accordingly to the window deadline. In the first experiment, the graph on the left, we compare the latency of the algorithms against varying the number of deployed YSB queries. We can see that for one YSB queries, most of the algorithms perform similarly on a second scale, with differences only on a sub-second scale. For 40 queries deployed, we can see here that Klink scaled significantly better than other algorithms. Furthermore, there's a 30% latency reduction here. For 80 queries, there's a significant reduction of latency of 50% from Klink compared to the most performing algorithm other than Klink. Specifically, there's a total of 7 seconds reduction of latency. The graph on the right, we present the cumulative distribution function of obtained latency to better visualize tail. Tail latency can be observed at 90, 95, and 99% levels. Here you can see that Klink scales significantly better than other algorithms. Specifically, Klink records latency drop from 20 seconds to 8 seconds, 70% reduction. You can also notice performance difference when running Klink with memory management and Klink without memory management. The memory management algorithm managed to reduce tail latency by 20% due to minimizing resource contention. As for throughput, measured by number of events processed per operators per second, we assess this quantity while varying the number of deployed queries. At 60 queries, you can see that Klink managed to scale significantly better, processing almost 3.2 million events per second, while other algorithms limited due to memory contention to 2.5 million. This could be observed through comparing Klink to Klink without memory management. Finally, we assessed Klink resource consumption, including memory and CPU utilization. In this experiment, we collected these data every quarter of a second and plotted the numbers. Blue and red dots are specific to memory, and they compare Klink with the default, where no scheduling algorithm is employed. Orange and black are specific to CPU utilization, where we also see Klink versus default. First, we will be focusing on the memory utilization. Here in this stage, observe that Klink memory consumption is linearly increasing. This is because Klink is optimizing to process events that minimize slack and not memory management. Therefore, more events are being ingested than being reduced in the operators. Then, when memory utilization reaches a peak, we start to notice a drop in utilization. This is due to memory management algorithm kicking in after reaching a high threshold of utilization. Also, you can notice how effective our scheduling algorithm is by assessing the rate of the drop. Memory utilization drops at different levels. Specifically, as can be seen here, it could drop to 20.5 gigabytes or all the way down to 7.5 gigabytes. This is due to the state of the pipeline, where different events are grouped at different operators. And next, we compare CPU utilization. You can see that Klink in black maintains high level of CPU utilization compared to default in orange, implying that Klink better utilizes the available resources and spends more CPU cycles at processing events than default. In summary, Klink employs 3 different mechanisms. First, a predictive algorithm that estimates the watermark ingestion time based on periodicity and network delays encountered. Then, a real-time deadline scheduling, whereby, based on the estimated ingestion time of watermarks, we prioritize queries based on the least slack policy. And third, an efficient memory management algorithm. And as we have just seen, that intelligently selects queries that reduce memory the most. Klink achieves 60% latency reduce and 20% throughput increase. More results about Klink can be found in the tiny URL, tinyurl.com/klink21. Thank you for your time.